In Algebra 2, there's this concept of parent functions and their transformations. Throughout this year, we're going to look at a variety of new functions, or at least functions that are new to you. And we want to see what they look like and how they transform. Right now, I want to start with just 4 kind of basic parent functions. We're going to take a look at their shape and identify their domains and ranges. First, let's start with the constant function. That is f of x equals a, where a is any constant, any real number. Now, how do you graph when you don't know how to graph? Well, you start plotting points. We're going to pick some x's, like 0 and 1 and -1 and 2 and -2. Find out what their y values are, their functional values, and then plot those points. Now, with f of x equals a is any sort of constant. So let's just, for example, let a be like 2, right? And say that f of x is equal to 2. Then when x is 0, f of 0 is 2. So we're talking about the point 0, 2. When x is 1, f of 1 is 2. So 1, 2. At -1, it's 2. At 2, it's 2. In fact, the functional value is always 2. So whether we're talking about 1 or 2 or -1 or -2, those functional values are all at 2. So when we graph that function, we end up with this horizontal line. Now, if we change that from being a 2 to being, I don't know, let's say -3. Well, then no matter what the x-coordinate is, the y-coordinate is -3. Always. And when we graph those points, we'll be down here at -3. So again, we'll end up with this horizontal line. In fact, no matter what the constant is, if this constant is a, the y value will always be a, whatever that value is. So we will end up with a horizontal line running through the y-axis at wherever a is. So when we're trying to identify the domain and the range, the domain, we could pick any x values we want. So we would say that the domain is all real numbers. But the range, what comes out, when we look at all of these y values over here, the only value that's going to come out for the range is whatever a is. Next is the identity function, f of x equals x. So if we were, again, to pick a bunch of x's and find out their functional values, well, with the identity function, f of x is equal to whatever x was. So if x is 0, f of x is 0. If x is 1, f of x is 1, and so on. It's the identity because whatever we put in is exactly the same as what we get out. So if we were to graph that function, we'd start at 0, 0, the origin, then 1, 1, -1, -1, 2, 2, -2, -2. And we obviously get another line. This one is what we call an oblique line. It's not horizontal, it's not vertical, it's tilted, right? But what we know about slope-intercept form, that if we were dealing with f of x equals x, that's like 1x plus 0. So this line has a y-intercept at the origin and a slope of up 1 over 1. And we get this line. Now when we're talking about domains and ranges, again, x can be anything we want it to be. It can be positive, negative, 0, fractions, decimals, square roots, it doesn't matter. And since it's the identity that whatever we put in is exactly the same as what we get out, the range is also going to be all real numbers. Now, we've already been graphing the absolute value function, but it should be included with these basic parent functions, just like those horizontal and oblique lines. And remember, with absolute value, its piecewise definition is that absolute value of x is x if x is greater than or equal to 0. And it's the opposite of x if x is less than 0. So to graph each of those lines, we're going to look at f of x equals x. And we just said that that's going to be a line 1x plus 0 with a y-intercept at the origin and a slope of 1. So that is the f of x equals x part. But looking back at the piecewise definition, it only equals x if x is greater than or equal to 0. Well, on the x-axis, 0 is right here. And then being greater would be talking about x being 1 or 2 or 3. So we're going to keep the piece of this line that is to the right of the origin and erase everything that's to the left. So erase that part. And now we can deal with the second part of our piecewise definition. That is that f of x is equal to the opposite of x. So that's going to be a line with the slope of -1, but also having a y-intercept of 0. To graph that line, it's going to have a y-intercept of 0, slope of -1 like this, but it only equals -x if x is less than 0. So on our x-axis, 0 is right here. We're going to be less than that, so -1, -2, -3, -4. That's the side of this line that we're going to keep. So we'll erase the stuff that is to the right of the origin. And we get this distinctive V shape of the absolute value where the vertex, that's that point where it changes direction, that vertex is at the origin, and each side has a slope of 1 or -1. As far as domain and range goes, we see that along the x-axis, we can use any kind of x's that we want. It's going to stretch forever in the x direction, left and right. So our domain is all real numbers. But as far as the range goes, our vertex is at the origin and the graph goes up. So that means that our y values, the f of x's, are going to be greater than or equal to 0. And we know that because absolute value only will, no matter what kind of number you put in there, the only number that's going to come out is going to be 0 or positive. The last parent function I want to look at is called the quadratic function. F of x is equal to x squared. So again, let's pick some points, pick some x's, find some y's. When we square each of these x's, f of x is going to be 0 squared, which is 0. F of x is 1 squared, which is 1. And when x is -1, you guys get this wrong in your calculator all the time because you type in -1 squared. But we need to square the -1, which means taking -1 and multiplying it by itself. Negative times negative should be +1. So when we square 2, we get 4. Squaring -2 will also give us 4. Now, when we plot these points, we're going to start at the origin, 0, 0. Then I got 1 and -1, 2 and -2. For 1 and -1, the functional value is +1, right here and here. But at 2, we're at 1, 2, 3, 4. Up here and up here. Now, it might look like a line, like a straight line on either side, very similar to absolute value function. However, if we continue to 3 and -3, then those functional values are going to be 9. So instead of 4, we're at 5, 6, 7, 8, 9, way up here. Now, when we connect those dots, we begin to see that distinctive U shape that comes out. Like that. I'm cleaning up just a little bit right here. But this distinctive U shape is called a parabola. It also has this point where it turns around, where instead of going down, it turns around and starts going up. It's also called a vertex. Its vertex is at 0, 0. When we think about domain and range, we can square any real number, whether it's positive or negative, 0, decimals, fractions, it doesn't matter. So the domain is going to be all real numbers. And the range is very similar to what we were dealing with absolute value, because our vertex is at the origin and the graph goes up from there. That means our range is going to be f of x is greater than or equal to 0. What you need to remember are the four basic parent functions. The constant function is f of x is some sort of constant number. It's going to be a horizontal line. The identity function is the same thing that you put in is what you get out. So f of x equals x. It's going to be an oblique line, y-intercept at 0, slope of positive 1. Absolute value is absolute value. That's where we get a V shape. V for value, absolute value. And then quadratic function is f of x equals x squared. And that's where we're going to get that parabola, that U shape.